Alright, so in this video we are going to finally start doing some calculus with these functions of several variables. And we're trying to generalize the idea of the derivative and the integral from Calc 1. So we're going to start with differentiation. So this whole chapter 14, this kind of long chapter, is just all about derivatives and the different ideas we can get from that. So let's think about a specific example here. The volume of a cone depends on the height and the radius. So we have v as a function of two variables, r and h. So it's 1/3 pi r squared h. So we could ask the question, how fast is the volume changing? This is what a derivative is from Calc 1. Remember that a derivative is an instantaneous rate of change. It's saying how fast is one quantity changing with respect to another quantity. The problem with functions of more than one variable is when you're asking how fast is it changing, you have to say, well, with respect to what? If I'm going to compare how fast two quantities are changing, if there's two independent variables, it's not clear exactly what I mean by that question. So am I calculating the rate of change as the radius changes? So, how fast does the volume change if the radius is changing? Or is it with respect to how the height is changing? Or maybe I'm changing both of them in some combination somehow that I haven't specified. So I really need to clarify this a lot more to make sense of what this derivative idea is going to mean. So one way that we can try to address this is to say, okay, I want the rate of change. What I'm going to do is fix the height to be constant. So you're not allowed to change the height of this cone, but we can change the radius. So the radius, the base, the circular base, could be really small, or it could be medium, or it could be, super big as you want. So we're allowed to change the radius, but always has to stay the same height. By doing that, what we've done is we now have a function of just a single variable. So there is no independent variable h, there's only one independent variable r. So the way we could do is write this. We could say v of r comma h naught is equal to f of r, which is equal to, so it's going to be 1/3 pi r squared h naught. So remember here that this h naught, this is a constant. So it's just a number. Now, we don't know exactly what number that is, but it's still just a constant. You can think of it almost like a parameter. Okay, so we've got a function of one variable. Now we can differentiate this like we did in first semester calculus. In other words, we can take df dr. Okay, so the derivative of f with respect to r, which in this case would be, so 1/3 pi and h naught. So those are all constants. And then the derivative of r squared is 2r. So we end up getting 2/3 pi h naught r. 2/3 pi h naught r. Now, if we remember that this h naught was only fixed for a moment, we decided to fix it. Here's the key. We can go back and then make that h naught not fixed anymore. So we can pretend that it really is another independent variable. So if we do that, that's when we get what we call the partial derivative of v with respect to r. And the notation that we use is this. So there's a couple different notations. There's this. There's also this. Okay, so these are the two main notations here. And just to be explicit about it, so what I could do is I could write partial v with respect to r of rh, just to emphasize that now, since you can think of it almost like unfixing, if that makes sense. We're fixing the height to start with, and then after we're done differentiating, we unfix it. We make it vary again. And so this partial would be 2/3 pi. I'm going to switch the order of r and h because it seems like more natural to put the r first. So 2/3 pi rh. So this is what we would call the partial derivative of v with respect to r. Now, we can go ahead and do the same thing in the opposite way. In other words, we could go ahead and say, let's fix the radius. So now the base has to stay the same, but I can change the height. I can make this cone as tall as I want or as short as I want. So just kind of mentally imagine what those different possibilities would look like. And now, since it's going to be a function of just the height, I could differentiate with respect to the height, and I would get the other first partial derivative, the derivative with respect to height. So in this case, we get v of r naught h, because we're fixing the radius. So let's call it, say, g of h. So in this case, it would be 1/3 pi r naught squared h. Okay. So all of this stuff here, the 1/3 pi r naught squared, that's all a constant. In particular, remember that this r naught is now a constant for the moment. We're going to differentiate this with respect to h. That would give us dg dh. And since this is all just a number times h, this is like saying what's the derivative of 5h, so it's just the constant. So it's just 1/3 pi r naught squared. But again, we're going to let r naught vary, and so we're going to get another one of these partial derivatives. Now, in this case, so there's no h in here, but we're just unfixing the radius. So in this case, the partial derivative only ends up being a function actually just of the radius. So we could say this is the partial with respect to h. The other main notation would be v sub h, and in particular, the partial of v with respect to h would be a function. So it says it's a function of r and h, even though we really know that it doesn't depend on h. We can still think of it as a function of r and h. So in this case, it'd be 1/3 pi r squared. Okay. So let's make these ideas a little bit less abstract. It still might seem, since we're dealing with general function here, not specific numbers, it may seem a little abstract to think about what exactly this is saying. So let's take specific values for r and h. So let's take the radius r to be equal to 2 and the height h equal to 3. Okay, so let's write down just some of these things, and we're just going to interpret, just talk through what each of them means. So what is v of 2, 3? Well, since the volume is 1/3 pi r squared h, it's going to be 1/3 pi 2 squared times 3. So let's see, that's going to give us 4 pi. And so let's just put some units to this. So it would be cubic, let's just say it's cubic units. Say these are all measured in the same units. So what exactly does this mean? So the interpretation of this is just saying it's a function. So this is just saying that a cone with radius 2 and height 3 has volume 4 pi cubic units. All right, so that's one thing to note. What about the following? So what about, what's the partial of v with respect to r at 2, 3? So first, the numerical value of this. So we said that the partial with respect to r was 2/3 pi rh. So 2/3 pi rh. So in that case, this is also 4 pi, but the units are different. So in this case, So it's the same rule as for Calc 1. The units for a derivative in Calc 1, it's always the units of the dependent variable divided by the units of the independent variable. So here, it's the same thing. So it's cubic units divided by units. So it's just 4 pi square units, which is really, secretly, it's cubic units per unit. And what's the interpretation of this? So what this is saying is the instantaneous rate of change of the volume with respect to the radius is 4 pi square units. In other words, I could approximate the change in the volume by taking the little change in the radius and multiplying it by 4 pi, and that would be a good approximation to the change in the volume. That's how fast the volume is changing with respect to the radius. And the last thing we could look at would be the partial with respect to height at 2, 3. Now the partial with respect to height was 1/3 pi r squared. So we got 1/3 pi 2 squared. So this is 4 pi over 3. It's also, the units are square units. And it's also still, secretly cubic units per unit. But what this is saying is, this is the rate of change of the volume with respect to the height. In other words, if I change the height a little bit, if I change the height a little bit units, then the volume is going to change by 4 pi over 3 times that. So, you could say at 2, 3, if I wanted to increase the volume, I'm going to get a lot more bang for my buck by changing the radius. Because for every little change in the radius that I give, that's going to increase the volume 4 pi times that. Whereas if I change the height that much, it's only going to change it 4 pi over 3, 1/3 as much. So for this value of r and h, changing the radius changes the volume faster than changing the height the same amount. Okay, so that's what that's saying. So this leads into the definition, so the actual definition of a partial derivative. So to define this, we need to assume that we're starting off with a function of 2 variables. So we're going to say let f of x, y be a function of 2 variables. And we should also include, so that this is defined for points near AB. I don't want to get too deep into the weeds about the technical issues about where this has to be defined. Let's just say it's defined, for all the points near and some little circular disk around the point AB. So then the partial of f with respect to x at AB, which can also be written as f sub x of AB. So this is equal to the limit. So this is going to look very much like an ordinary Calc 1 definition in terms of the limit of a difference quotient. So the limit as h goes to 0. But now when I do the numerator, I'm only going to add the h to the x variable, so only to the first coordinate. So I'm going to say x plus h. Sorry, it's going to be a plus h, comma b minus f of ab. So notice what's happening here. I'm looking at the value of f at AB, and then I'm looking at the value of it somewhere away from there. But I'm only changing the first coordinate. I'm only incrementing a from a to a plus h. B is staying constant. It's the same thing in each one. And then I'm dividing by h. So it's an ordinary difference quotient. Only difference is I'm just changing the first coordinate. And of course we get a similar definition for the partial with respect to y. So this is f sub y at AB would be the limit as h goes to 0 of f of a b plus h, minus f of ab. So the only one we're changing here is the second coordinate, not the first. Now there's lots of different notations for these. So I've already introduced the two main ones. There's a couple more I think that are important. So there's the kind of D notation, so the Leibniz notation. You use this, it's not a D though, it's kind of like this del symbol. You still say D, so like this is, df dx, df dy. So this is the Leibniz notation. For functions of two variables, this is also often written partial with respect to x of something. So especially if you wanted to include like the two independent variables, you could write it like this. You could also put z. So z is common because it's on the function is graphed on the z-axis in the z direction. So partial z with respect to x or partial z with respect to y, and so on. Those are also super common. Then there's a subscript notation, f sub x, f sub y, and also you can include the variables here. So you could say f sub x of xy, or f sub y of xy, if you wanted to emphasize what the independent variables were. Sometimes numbers are used. So in place of, especially, this is really the case if there's like, you could have something you're modeling that's a function of 6 or 7 variables. So you're going to run out of letters. So if there's many variables, you might also use something like, f sub 1 or f sub 2 and so on. Or maybe d1 f, d1 2. We're not going to use these too much. So we're not going to use these much. That would be mainly if you go beyond. If you could go beyond 3 variables, beyond x, y, z, that's probably where you might start using this. So not going to use much, if at all. This D notation, that is important, like in differential equations, because that's kind of like an operator notation. Now there is another, so if it's dxf or dyf, we're still not going to use that, I don't think, in this class, but that is something that you might see if you take Math 4. Differential equations, that's not uncommon, to indicate partial derivatives with this D notation, like an operator notation, but with the subscript. Now let's talk about how we actually calculate these. We're going to go through several examples, and you should have picked this up from the example with the volume of a cone earlier, but just to spell it out to be really clear. So the process you want to go through to calculate derivatives is the following. So you want to first, whoops, just a minute. Sorry about that. So first, to differentiate, so to find, say, the partial with respect to x, fix or hold y as a constant, and differentiate the ordinary Calc 1 derivative with respect to x. So just what we did above. If you want to find the y partial, fix or hold x constant, and differentiate with respect to y. Now, I haven't talked about functions of more than 2 variables, like 3 or more, but much the same thing would hold. I'll do one example later. But basically, if you want to differentiate with respect to one of the variables, you hold all the rest of them constant. So say you had a function of, I'll just kind of put a quick example here. Say we had w was a function of x, y, and z. Then if I wanted to know what's w sub x, I would fix y and z constant and just differentiate. So the point is you hold all the other ones constant and you only differentiate with respect to the one that you're taking the partial with. That you're taking the partial with respect to. All right, so enough with the definitions and notations. Let's go through some examples to get a feel for these. So what we're going to do for each of these functions is we're going to graph, well, first we're going to calculate the partials, and then evaluate them at this particular point AB that's going to be given, and then we're going to graph these at the CalcPlot 3D. And there's a nice feature on there, I did look into it and remember how to do this, where you can actually see the geometric interpretation of the partial derivatives. The geometric interpretation of these, so let's just talk about this for a minute. Just on the side here. So we've got a function of 3 variables. We're graphing it in, sorry, a function of 2 variables we're graphing in 3 dimensions. And we know that the graph of one of these functions is some kind of, surface. So let's say that this is the point AB, let's say it's right here. And then we go up to, let's say it's right about there. So that's going to go up to this point up here, which would be the function value. So it's going to be the point with 3 coordinates a, b, f of a, b. Now, what does the x partial mean? What it means is we're slicing it with a vertical plane, and when that vertical plane, so the vertical plane is y equals b. So that vertical plane looks something like this. And the intersection of that with the graph ends up being a one-dimensional curve. So let's say it looks something like this. Okay, so maybe that's what the curve looks like when I intersect it there. Then what the partial is saying is, what is the slope of this this curve? What's the slope of the tangent line to this curve? That's really all it's saying. So it's just saying, if I take this, what is the slope of the tangent line here? And the same thing is true if I look at the other way. If I fix x and I change y, I get a perpendicular vertical plane. Maybe it's cutting it, let's see. Okay, so we got a plane like this cutting it, 90 degrees to that. And that's going to intersect it in another type of curve. Let's say like this. Then this is just saying, the partial then with respect to y is just saying what's the slope of that tangent line. So that's kind of the general picture we're going to see when we go to the graphing software. So let's look at, so first of all, let's rewrite f of xy here. So to take the derivative, let's write this as 4 minus x squared plus 3y squared all to the 1/2. Now you should pause the video, think about what this is going to look like. This is actually one of the quadric surfaces. If I square both sides, let this equal z. If I square both sides, then I would get x squared minus 3y squared plus z squared would be equal to 4. So that's going to be a quadric surface. So think about which quadric surface that is. But let's go ahead and differentiate here. So let's differentiate with respect to x. We get 1/2 all this to the minus 1/2 times the derivative of what's inside. Now, up until now, we haven't had to worry about with respect to what. But now that we're taking a derivative of what's inside, we do have to think that it's with respect to x. There's only one term that has x in it. The 4 and the 3y squared are both constants. So it just ends up being minus 2x. And we can simplify this then to just get minus x over square root of 4 minus x squared plus 3y squared. So that is the partial with respect to x. The partial with respect to y starts off the same, so I still start off with a 1/2 4 minus x squared plus 3y squared. Sorry, this should be, to the minus 1/2. But now when I take the derivative of what's inside, it's only with respect to y. 4 minus x squared is a constant, so I get 6y. So that ends up giving me 3y, positive 3y, over this square root, 4 minus x squared plus 3y squared. Okay, so those are the two partial derivatives. And now let's go ahead and see what this is at the specific point 0, negative 1. So the partial with respect to x at 0, 1. Okay, so I have to plug in 0 for x and 1 for y. Okay, so that's just going to end up being 0, right? It's a 0 over square root, you know, 7 or something. But it doesn't matter what's on the bottom, it's still 0. And the partial of f with respect to y at 0, 1 is going to be 3 times 1, so it's going to be 3 divided by square root 4 minus 0 squared plus 3 times 1 squared. Okay, so it's the same square root 7. So it's 3 divided by square root 7. 3 divided by square root 7 is about 1.13. So that's what we expect to see here. We expect to see a tangent line in the x direction of slope 0, and a tangent line in the y direction of slope about 1.13. So here's what the graph looks like. You can see there. So this is a hyperboloid of one sheet, but notice it's only half of it. So there would be another half that's symmetric below the xy plane, but it's not there. Now, what I can do here, I'll show you. So if you enter this in z is equal to this, if you go up to here, the third button here, what you can do is, if you click on here, notice I can move around. So what this is doing is this is the point in the xy plane, and then the point will bounce around on the graph. So we're at the point 0, x equals 0, negative 1. You know, I think I did 0, 1 before. I'll go back and change that. It's a very minor thing. It just changes the sign on the y partial. So we're at 0, negative 1 here. So we said that so let me show you in the x direction. So I'm going to toggle this, and I'm going to do show, so this fx trace tangent line, that's showing you the intersection of this with the plane y is equal to negative 1. Okay, so see there that red? That's when y is equal to negative 1. You can see there, y is equal to negative 1. It cuts the graph in a one-dimensional curve. And at that point, so remember now towards us is the positive x direction. So you can't read it this way. To the right is not positive, actually to the left, the way we're looking at it. It has derivative 0 here. And you can kind of see that. It reaches a local maximum there, it looks like. Now what I'm going to do is change the x. So I'm going to switch x back and forth. And what you'll see is, you'll see the tangent line change, just like this was an ordinary function of x. So see, as I move it this way, I'm moving along this curve. Okay, and then I decrease it back down. Okay, so as I move along this curve, I'm changing that tangent line. The slope's changing. So we're just saying, okay, right at, sorry, I changed this one as well. Should be at negative 1. So what we're saying is right at 0, that line, tangent line, has slope 0. That's what that's saying. Now if I go ahead and change it to the y partial, it goes the other way. I'm fixing x now. X is equal to 0. So I'm looking at the part of the graph that's above the y-axis. And now I'm saying, what's the slope of this? Now, when I did it the first time, I did it at 0, 1. I wanted to do it 0, negative 1. So we said it was 1.13, so it should be negative 1.13. And you can see here, this does have a negative slope. As y is increasing, that's definitely negative slope. So as I change y now, you can see the different tangent lines going this direction. So it's just saying, what's the slope of the tangent line here at negative 1? Now, if I wanted to look at what I can do here is I could change x here, and you can see that. So what this is doing is this is saying what's the value of the partials as I change x. So now I'm fixing y equal to -1, but I'm looking at all the different partials. You could ask that. So these are all the different slices that determine the y partials. But then I could also look at, by the same token, I could go and change this to the x partials we were looking at before, and now change x, and you can, now change y. And you could see all the different, now you can see all the different intersections that would yield us partials with respect to x. So it's these vertical planes parallel to either the xz plane or the yz plane that are cutting the graph, intersecting in a curve, and then the partial derivative ends up being the slope of the tangent lines at that point. Okay, I need to fix this to make it -1. All right, that was pretty painless. Good. So let's go on to the next one. So this is actually the default function set up on CalcPlot 3D. When you first open it up, it has z is a function of x and y, and this is the function that they use kind of as their template, the one that you look at that looks nice. So 7xy divided by e raised to the x squared plus y squared power. So let's calculate the first partial with respect to x. Okay, so for this one, it probably is best to use the quotient rule. So we're going to go denominator, derivative of the numerator. Let's leave out the 7 for now, because we know that's just a constant that's going to tag along. The derivative of the numerator, xy, with respect to x is simply y, minus the numerator minus derivative of the denominator. So that would be xy times the derivative of e to the x squared plus y squared, which is e to the x squared plus y squared, times another factor of the derivative of x squared plus y squared, which is going to be 2x. So we pick up another factor of 2x, and this is all divided by e to the x squared plus y squared all squared. Okay, so let's see what we can do with this, and then let's not forget, well, we'll tag on the 7 at the very end. Let's see if we can clean this up. I could factor out an e to the x squared plus y squared on top. And I've got y. Actually, I can factor out a y. So let's go ahead and do that. I'm left with 1 minus 2x squared. 1 minus 2x squared, all divided by, let's see, e to the x squared plus y squared, all squared, and then of course there's e to the x squared plus y squared that cancels, so that cancels with that. So it looks like we get y times 1 minus 2x squared all over e to the x squared plus y squared. And now I'm going to put in the 7. So 7y, 1 minus 2x squared divided by e to the x squared plus y squared. So this means that the partial with respect to x at 1, 1 will be equal to, let's see, 7 times 1 times -1. So it'll be -7 over e to e squared. Okay, so -7 over e squared. That's about minus 0.95. So just a little bit bigger than -1. Now, a nice thing about this function, if you notice, it's what we would call symmetric in x and y. In other words, if I interchange the role of x and y, I get exactly the same function. 7yx over e to the y squared plus x squared would be exactly the same function. So what this means is, I don't really need to calculate the partial with respect to y, I just need to interchange x and y in the partial with respect to x. So the partial with respect to y is going to be 7x times 1 minus 2y squared over e to the x squared plus y squared. Okay, save myself some work there, which also means the partial with respect to y at 1, 1, since it's 1, 1, x is equal to y there, it's also going to be the same minus 7 over e squared, or it's also going to be minus 0.95. Now let's look at the graph here. Okay, so and you can see here, if you didn't notice this here, it has the value of the partial at the top. So you can read off f sub x at 1, 1 minus 0.9473. And there's the point there. So this is the x partial. So that's about -1. That's the slope of that tangent line. And if I move x around, you can see this changing. So it's saying this particular graph, this function of one variable here that I get, which is the intersection there, what's the slope of that line when x is equal to 1, right there? That's what it's equal to, and if I change it around, it's going to be pretty much the same thing because it's symmetric in x and y. I just get this way, but you can see it's the same value. Okay. All right, let's go on to the next one. Let's change up our notation a little bit just to start getting used to it. So I'm going to say f sub x of xy. Now, in this case, since this is a function of x multiplied by a function of y, this is going to be extremely easy to calculate the partials, because all I have to do is just calculate the derivative with respect to x of the x part, and the function of y just tags along as a constant. So in fact, since the derivative of x cubed is 3x squared, I just get that the derivative of this is 3x squared e to the minus y. Okay, not much to do there. And then for the other way, it's going to be the partial of f with respect to y. I need to just differentiate the e to the minus y. So that'll be e to the minus y, but then I pick up another minus sign, so minus x cubed e to the minus y. And I want to evaluate these at 2, 2. So I'm going to get f sub x at 2, 2. So that's going to be 3 times 2 squared e to the minus 2. So that's, let's see, or it's 12 over e squared. And so I'll figure what that is in a second. The y partial, I'm going to get minus 2 cubed times e to the minus 2. So that's going to be -8 over e squared. Okay, so let me get the approximate values for these. Okay, so let's go ahead and look at this graph at the point 2, 2. So there's what the graph looks like. Kind of a weird graph. Let's see. Let's back up maybe a little bit. Okay, so it doesn't change too much if you keep backing up. All right, so let's look at, we were at the point 2, 2. So let's go to the point 2, 2. Actually, we need to back up here. There we go. Okay, so at the point 2, 2, so you can see. So I believe we're looking at the y partial. Let's look at the x partial first. Okay, so you can see as x is increasing, that is, so it looks negative because we're looking at it the other way. Let's look at it this way. So this is from the perspective of x is increasing to the right. You can see there it definitely, whoops, sorry. I don't know how to get this. There we go. You can see there it definitely has a positive derivative as x is increasing. Okay, so if I change x here, you can see there. So, whoops, I don't know why it did that. You can definitely see there it's increasing at 2. Now if I change it to the y partial, that's the minus 1.08. Now you can see as y increases, okay, so there's the direction of increasing y. You can definitely see that it's decreasing in the y direction. Right, it's decreasing. Okay, let's go to the next one. Okay, we've got one with a trig function here. This is x times cosine of pi times x minus y. So partial with respect to x. I have to use the product rule here, so it's going to be first times the derivative of the second, so minus sine of pi x minus y, times the derivative of what's inside. Now, the derivative of what's inside is going to be pi times the derivative of x minus y. So with respect to x, that would be just pi. So I just pick up a factor of pi here. Plus the second, cosine pi x minus y, times the derivative of the first. The first is just x, so that derivative is just 1. So that's just times 1. Notice that this function is not, so the cosine part actually is symmetric in x and y, but the x outside makes this not symmetric in x and y, so I can't do what I did on the second one. Let's clean this up a bit. I think I get a minus pi x, so we get a minus pi x sine of pi x minus y plus cosine of pi x minus y. The main reason I put the factor of pi in here is just so that I could put integer values in for a and b, so it's easy to evaluate. Let's look at the partial with respect to y. Partial with respect to y is first, derivative of the second, so start off just the same. But now, when we get to the derivative of what's inside, it's going to be a minus pi, because we're differentiating with respect to y. So minus pi, plus second derivative of the first. Now the second, actually I guess I didn't even, sorry about this, I didn't even really need to use the product rule because x is a constant here. I could have just differentiated. I could have just said it's x times the derivative of the cosine, but if I continue with the product rule here like I did above, I'd get plus the second derivative of the first, but the derivative of x with respect to y is 0. So it would have been better if I just remembered from the beginning here that this x is a constant with respect to y. Then I just would have gotten x times, I would have just gotten the first term. So let's clean this up. And since there's 2 minus signs, I'm going to get positive pi x. So just positive pi x sine of pi x minus y. Now we need to evaluate these at 0, 1. Okay, so let's see here. Partial with respect to x at 0, 1. I'm going to plug in 0 for x. Okay, that's going to eliminate the first term entirely. Great. And then I plug in 0 for x and 1. So I'm going to get cosine of pi 0 minus 1. Okay, so I get cosine of minus pi. Cosine of minus pi is negative 1. So I get negative 1. And the partial with respect to y at 0, 1. There's only one term, and it also has a factor of factor of x. So it's just 0. So partial with respect to x should be negative 1. Partial with respect to y should be 0. So here's the graph. You can see the periodicity of it in both directions, right? So if I were to let me back up a little bit, you can see here it's definitely periodic. So what we're looking at here is the x partial. You can see there it says negative 1 up there, and you can definitely see here it's negative 1. Again, remember when you're reading from the first, when you're viewing from the perspective of the first octant looking down, the positive x direction looks like it's going to the left. It's very counterintuitive, but that's the way it is. So this is a negative slope here. Let's see, so that's there. It's increasing, decreasing, increasing, and so on. Okay, let's go to then the y partial. notice actually it's exactly straight there. So what that's saying is when you fix x equal to 0, the function is identically 0. So of course the derivative, the partial, is going to be 0. The graph just intersects the y-axis. Okay, last one that will calculate these and then look at the graph. Natural log of x squared plus y. So if you remember, the derivative of natural log is 1 over what's inside, so 1 over x squared plus y, times the derivative of what's inside with respect to x, that's 2x. So I get the x partial is 2x over x squared plus y, which means the x partial at negative 1, 1 will be negative 2 over 1 plus 1, which would be negative 2 over 2, negative 1. Okay, so I get another partial equal to negative 1. The partial with respect to y, again, 1 over x squared plus y. But now I differentiate with respect to x inside the log, and, with respect to y, the x squared is a constant, so I just get the derivative of y, which is 1. So this just ends up being 1 over x squared plus y. And at negative 1, 1, that's 1 over 1 plus 1. So it's equal to 1/2. So I get an x partial of negative 1, a y partial of 1/2. All right, let's take a look at this one. This will be the last one that we look at the graph for. So I actually believe that we looked at this graph before. Let's see. Let's go into the first octant. Okay? So there's the first octant. So looks something like this. And maybe we looked at natural log of x squared minus y. It's very similar kind of shape. Okay, and we were looking at the point negative 1, 1. So let's go in here. Negative 1, 1. Okay, so right there. So if we look at the x partial, this is the y partial line. Switch it back. So the x partial there. So notice we get partial equal to negative 1, which you can see there. That has about a slope of negative 1. It says negative 1 up there. If I change it to the y partial, boom, that has positive slope 1/2. Okay, so we've hopefully with these 5 examples and you seeing these intersection curves and the tangent lines, it really is giving you some geometric intuition into what the partial derivative means. All right, I just wanted to go over one example of a function of 3 variables just to show you that the ideas carry over pretty easily. You don't have to really change your perspective much. The only difference is if you're finding one of the partials, you have to hold all the rest of the variables constant. So for instance, if I'm going to find the partial with respect to x here, I'm going to fix y and z to be constant. Okay, so that would give me now the x squared sine of y plus z. The sine of y plus z is all a constant. So this is just 2x sine of y plus z plus, now the z is a constant, so I do get z over, now the arctangent would be 1 over whatever's inside squared, so 1 plus x squared y squared, but then I have to multiply by the derivative of what's inside, which would be y, so times y. So altogether I would get 2x sine of y plus z plus yz over 1 plus x squared y squared. For the y partial, let's think about the y partial. Now the x squared is a constant, so I get x squared cosine of y plus z. I do have to think about the derivative of what's inside, but the derivative of y is just 1. So it's really times 1. And then over here, the z is a constant. So actually I'm going to get the same thing I got before, except instead of picking up a factor of y, I'm going to pick up a factor of x. So it's going to be xz over 1 plus x squared y squared. And the z partial, let's see. Now I've got x squared. I still got cosine y plus z, just like before. But now, all the inverse tangent of xy, that's all a constant, times z. So I just get that constant, so plus arctangent xy. Okay, so those are the partials here. All right, so for this problem, it says the ellipsoid 6x squared plus 5y squared plus z squared equals 12 intersects the plane y equals 1 in an ellipse. We want to find parametric equations for the tangent line to the ellipse at the point 1, 1, 1. So the key to this problem is realizing it's just asking you for the equation to the tangent line that we've been looking at this whole video. So let's just take a look at what this looks like. Okay, so there's the ellipsoid. So that's the 6x squared plus 5y squared plus z squared equals 12. So we're intersecting this with the plane y equals 1. So let's go ahead and add that. We're intersecting that with y equals 1. Okay, there we go. So you can see the intersection there. So imagine that's going to intersect in an ellipse. Now, if we want to think about this in terms of partial derivatives, what we need to do is think about the graph. That's the positive square root. If I solve for z and I take the positive square root, I get z is the positive square root of 12 minus 6x squared minus 5y squared. So let's take a look at that instead. So I'm going to do z equals positive square root 12 minus 6x squared minus 5y squared. Okay, so there's the same, that's just the top half of what we were looking at. And then we're looking at the y equals 1. So y equals 1 means we're fixing y constant and we're changing x. So we're looking at the partial with respect to x at 1, 1. Okay, so there, so see, that was what we were just looking at. That's the curve, that's the intersection. And so you can see here, now it says up here negative 6, so we should find that it's negative 6. So let's go ahead and actually compute that, and then let's make sure that that's what we get, and then let's think about what the parametric equations are going to be here. Okay, so we said we looked at z equals, it's 12 minus 6x squared plus, minus 5y squared. All to the 1/2, which means the partial with respect to x is equal to 1/2 all of this stuff to the minus 1/2 times the derivative of what's inside with respect to x, which would be minus 12x. And so if I evaluate that at the point 1, 1, right, because this is saying x and y are 1, which makes z 1. Then I get, so it's really minus 6x, so it's minus 6 times 1 over square root of 12 minus 6 minus 5. Okay, so that's negative 6 over 1. So there's where the negative 6 comes from. Now to think about the parametric equation here. Okay, so what we have to do is think of, we're in the plane y equals 1. So let's just kind of sketch over here. So this plane is y equals 1. And think of this as like an xz plane, okay? So in the xz plane, we've always got y is equal to 1. And we're looking at the tangent line of this, so we said we get an ellipse. So in fact, that ellipse is 6x squared plus z squared is equal to 7. If you plug in 1, subtract 5, you get that. So, okay, whatever this ends up being, let's see, if I divide by 7, that makes that 1. So it's a, you know, it's an ellipse, something like this. So some kind of ellipse like this. And we're at the point 1, 1 here. So say it's somewhere like that. And we're looking for the graph of, the equation of this tangent line along here. So let's think about how we would parameterize it. We could let x is equal to t, and then we just have to figure out what is z going to be in terms of x. Well, what would be the ordinary equation of a tangent line? So think about if you're doing just the ordinary equation of the tangent line. This would be at the point 1, 1 with slope -6. So it would be c is equal to 1 plus the slope times x minus 1. So that would be 1 minus 6x plus 6, or minus 6x plus 7. So that tells us we should take z equal to minus 6x plus 7. So we're going to have x equal to t, and z would be, well, this would be minus 6t plus 7. Okay, so those should be parametric equations for the line t1 minus 6t plus 7. Let me go ahead and write that here and circle it. T1 minus 6t plus 7. And in fact, I should be able to go back to the graph, and if I do this as a curve, a space curve, you should see that it matches exactly the tangent line. So let's go ahead and do that. Okay, so this black line there, so that should be the t1 minus 6t plus 7. So let's go ahead and graph it, and it should match exactly with that black line. Okay, so we're going to add a space curve, RT, which is going to be t1 minus 6t plus 7. Oh, and look, it's exactly the same. It matches up right with the tangent line there. So that's how you can find the parametric equations for the tangent when you, now here we cut it with a plane that was parallel to the xz or the yz plane. When we do directional derivatives later, we'll see that we can actually do it in any possible direction, not just ones that are parallel to those two planes. Okay, this is a long video, so this is a good place to stop. There'll be a much shorter section in the next video where we're just going to do the higher derivatives, so the second partials and the mixed partials.